Hello everybody. So today we are going to start talking about using this idea of integrating to find volumes. This is going to kind of follow along with the investigation activity that we did in class, and we're actually going to start by just running through some area formulas that we're going to need. So you may remember deriving these in class and actually seeing where these formulas came from. Right now what I'm going to do is just help you write them down so that you have them all organized in one place, and then if you have questions about where these formulas came from, I of course would be happy to help you derive them when I see you in class again. So the first formula we need to know is how to find the area of a square when we know that one of the sides is worth s. And what we decided in class was that the area would be s squared. Pretty straightforward. Then we also needed to know how to find the area of a square when instead of knowing one of the sides, we knew the diagonal. What we decided was that if we knew that the diagonal was worth a certain amount, we could say that each of the sides would be that number divided by the square root of 2, which means our area would just be the diagonal divided by the square root of 2 squared, which would give us diagonal squared divided by 2, which we usually write as 1/2 times the diagonal squared. Then we had talked about a semicircle, and we said for a regular semicircle we would normally say that the area is 1/2 pi r squared, but this time instead of knowing r we're going to know the diameter, so we're not going to know the radius. However, we did also say that the radius would just be half of the diameter, so we could substitute diameter over 2 squared, which would give us 1/8 pi diameter squared, which we would rewrite as pi over 8 diameter squared. Is sort of the more traditional way to write that. If we have an equilateral triangle, that means all three sides are the same, so this would be s. And to figure out the height, we would rethink about this as having a 30, 60, 90 triangle. Now this half would be worth a side divided by 2, which then to figure out the side opposite the 60-degree angle would be the square root of 3 over 2 times a side. So then if we use the regular area formula for a triangle, 1/2 times the base, which is s, times the height, which is the square root of 3 over 2, times s, we would end up with the square root of 3 over 4, s squared. If we had an isosceles right triangle where we knew one of the sides was s, because it's isosceles, we would know that the other side was also s, and then we could just use our regular area formula for a triangle, 1/2 times the base times the height, and we would end up with 1/2 s squared. Finally, if we had an isosceles right triangle where we knew the hypotenuse instead of knowing one of the sides, we could use the same idea we used with the diameter here, or the diagonal here for a square. Each of the sides would be the hypotenuse divided by the square root of 2, which would mean that if we use our regular area formula, we would have 1/2 times hypotenuse divided by the square root of 2 times hypotenuse divided by the square root of 2, which would be 1/4 h squared. So these formulas are the ones that you're really going to need to know sort of going into these problems. These are not formulas that would be given to you in the problem. You would need to know if this is the shape, this is the area formula. Again, if you are interested in seeing where some of these formulas come from more in depth, you can refer back to the derivations we did in class, or I'd be happy to, of course, go over that the next time I see you. So how would you actually find volumes using areas? Well, as we discussed in class, a lot of shapes can have the idea that there's a base shape, in this case a circle, and then we can slice it, and each of the slices would be the same. So these would all be slices who are squares. Now, when we do this, we call each of those slices a cross section, and your cross section can be perpendicular to the x-axis or perpendicular to the y-axis. If your cross-section is perpendicular to the x-axis, we say that we always integrate with respect to x. And if your cross-sections are perpendicular to the y-axis, we usually integrate with respect to y. So how would you set up these integrals? Well, to add up the areas of all of these cross-sections, we would use an integral from your left bound, because we're doing this with respect to x, so this would be the left bound. And the top number would be the right bound. And inside of here, we would put the area formula, just like one of these formulas we just wrote down. So this would be the area formula in terms of x. In other words, your area formula would not want to have an S or a D or an H in it. You would want an area formula that had X's in it, and then of course dx at the end. Now if we're going to set this up with respect to y, it looks very similar, only instead of using the left bound and the right bound, we would use the lower bound, because now y's go up and down, and this would be the upper bound. And then we would again put our area formula in here, but instead of being with respect to x, we would do this with an area formula in terms of y, and then dy, because this one's going to be all in terms of y. So how would this look? How would you actually execute this moving forward? So problem number 1 says the region bounded by the graph of y equals 2x minus x squared and the x-axis is the base of a solid. So we're talking about this region bounded by the x-axis and this graph as being the base of the solid. So this is like an overhead view. For this solid, each cross-section perpendicular to the x-axis is an equilateral triangle. Now, as we saw in our demonstration and our investigation in class, when you see these cross-sections from above, they're so skinny that they just look like straight lines. So in this case, all of the cross-section would be straight lines perpendicular to the x-axis, so going this way. And each of these is going to be an equilateral triangle. What is the volume? We're going to use a calculator for our final evaluation here to actually type it in and get our answer. So if I try to think about how to set this up, we're going to organize our work like this. We're going to start by saying what area formula we intend to use. Because each of the cross sections here are equilateral triangles, our area formula that we intend to use would be square root of 3 over 4 s squared. Now, the next thing we need to do is figure out what s is in this context. So what is s in this problem? Because each of the sides of the triangle goes from this function and stops at this function, we would do top minus bottom to get the length of each of those sides, which in this problem would be the function 2x minus x squared minus the bottom function, which is 0, and that simplifies to just 2x minus x squared. Now our third step would be to actually set up our volume integral. So we would integrate from our left bound, which is -1, to our right bound, which is +3. Inside of there, we would put our area formula. Now our area formula is the square root of 3 over 4 times side squared. But in this case, each of the sides will be 2x minus x squared, and then we would put dx. Now, because we have a calculator here, I'm just going to go ahead and type that in, and I'm going to see what I get. And when I do that, I get Math 9, integral from -1 to 3 of the square root of 3. Let me try that again. Math 9, integral from -1 to 3. Let me start by making a fraction of the square root of 3 over 4, and then parentheses 2x minus x squared, there we go, dx. And my answer should be 2.656. and that would be the volume of this figure that I'm building. Now what we're going to do is look at an example where we're going to integrate with respect to y. So the base of a solid is the region enclosed by the graphs of y equals e to the x, y equals 4, and the y-axis. Cross sections are perpendicular to the y-axis and are rectangles whose height is twice the length of the base. So because we're perpendicular to the y-axis, when I view these cross sections from above, they would all be running this way from right to left. So the first thing I need to do is establish my area formula. Now this doesn't say a shape that we listed like on the first page of the notes. It doesn't say that this is just a square whose diagonals are on the base or a semicircle. It says we have a rectangle with heights twice the length of the base. Now a normal rectangle would just be base times height. But in this problem it's telling me that the height is twice the length of the base. So I would substitute that in there, and I would get 2b squared. Here I had to sort of construct my own area formula. Now the second step would be to figure out, well, what is the base this time in terms of y? Because we're going with perpendicular to the y-axis. So I would need to do right minus left, which in this case would be this function minus 0. Now this function was y equals e to the x, but since I want everything in terms of y, not in terms of x, I would rearrange this and make it x equals the natural log of y. So my right function would be the natural log of y, and my left would be 0, so I would just have the natural log of y. Now the third step would be to set up a volume integral. So I would integrate from my lower bound, which is 1, to my upper bound, which is 4. And then inside of here, I would put my area formula. Now my area formula is 2 times b squared. And in this problem, b was represented by the natural log of y, dy. So then I would just type this in. So what I would do is I would go Math 9 from 1 to 4 of 2 times the natural log of, and because I'm typing it in the integral, it doesn't matter that I'm using x here, squared dx. It's just an arbitrary variable. And then I would have 5.194. Last but not least, problem number 3, we're going to set up this way. Consider the space bounded by y equals x squared in the line x equals 3 on the x-axis. Suppose a three-dimensional solid is made by making cross-sections perpendicular to the y-axis in the shape of semicircles. Now here, what I'm going to do is start by sketching a picture. So I happen to know what the graph of y equals x squared looks like, which is like this. It doesn't have to be a super detailed picture, it just has to be a visual representation of what we're doing. I know that the line x equals 3 is this vertical line. And I know that the x-axis is another one of my boundaries. So the region that I'm looking at is this going to be little, sort of like a triangle. It looks kind of like a curvy triangle. Suppose a three-dimensional solid is made by making cross-sections perpendicular to the y-axis. So because my cross-sections are perpendicular to the y-axis, they would run from left to right, and they would look like little lines when I'm looking at it from above. Each of these cross-sections is going to be a semicircle. So the area formula that I would use for a semicircle would be pi over 8 times the diameter squared. Now, each of the diameters in this problem is going to go from this function to here. So each of my diameters will be the right function, which is 3, minus the left function, which is x squared. Now, because I'm doing everything in terms of y, I would need to rearrange that, and I would just have the square root of y. And again, this was right minus left. Probably should have written that. I apologize. So the third step would be to set up our volume. So our integral would go from our lower bound, which is 0, to our upper bound, which is where x squared and 3 intersect, which is at 9. And my formula would be pi over 8 times the diameter squared, and then dy. In this case, the diameter is 3 minus the square root of y. I feel like I didn't do a very nice job explaining why this is 9. I should probably go into that a little bit more. So because this is x squared, and we know that this is 3, if I plug 3 into y equals x squared, I would get that they intersect at the point 3, 9, which is why I'm using the 9. It's the y value of the intersection point. That's the higher number. And y is the variable I'm using when I'm integrating here. So I want the low number, which is 0, to the high number. Then I'm just going to type that in on my calculator. So I'm going to have math 9 from 0 to 9. I'm going to have pi over 8. And then I'm going to have 3 minus the square root of x squared dx. Now I know that this problem is in terms of y. The reason I'm using x's in here is that in our integral, that's just an arbitrary variable. So my volume here would have been 5.301, and that would have been my final answer. Okay, thank you so much for watching. I hope this clears up the more procedural part of how to evaluate these. We kind of went over the conceptual part in class. Again, if you have any questions, I'm happy to talk with you about that and show you more in depth the concept that we're addressing here. But I hope that this does clarify the procedural part. And have a great afternoon.